Okay, thank you.
All right. Yeah, thanks so much. So my name is Tony Nowatsky, and today I'm going to be talking about an accelerator design framework that my research group, the PolyArc research group, has been working on over the last few years. And before we get started, we have to get started right away because there's a lot to do. But before we get started, actually, is my mouse going to work? Yes. So this is the tutorial website. So if you want to follow along with the examples, which we'll get to in about 20-25 minutes or so, you should follow the setup procedure on the website. It involves downloading a 1.5 gigabyte set of binaries, and so if you haven't done that yet, it'd be good to start. There's a couple links, so you can try and download whatever link works the fastest. If you have any problems, please let us know in the Q&A, and we will do our best to help you with the technical problems in real time if we can. And the sources are also available online as well. Okay, so before we get into things, let me try to, and while you're setting things up, let me try to motivate this design framework a little bit. So if we look at what's been happening in academia and industry, it seems like accelerators are the answer to all of our problems, right? So some folks at Harvard have been looking at accelerators on mobile processors over the last few generations, and they found that mobile SoCs have increasing number of accelerators, and all those have had to be designed and verified and so on, and that's a lot of effort. There's a huge amount of effort also in developing machine learning accelerators, and that's been very, very successful. And in part because there's a small number of kernels that you can that target a big part of the economic incentives behind machine learning. But it's harder if you want to target a broader set of applications or more difficult applications. And of course, there's a huge volume of research being devoted to accelerators right now. So it would be nice if we had good ways of developing accelerators in a principled way. Okay, so what about the existing ways of developing accelerators? What are they, and what might not be so great about them? Okay, so one kind of approach I would characterize as domain-specific design, right? So in this approach, you take, a human basically will look at a set of applications, try to discover what are the fundamental behaviors in those applications that can be exploited, and then develop hardware tricks and hardware design, a way to expose those domain-specific tricks through an ISA, and then develop a number of applications that run on that domain-specific ISA. Or if they're very advanced, they build a compiler for those. And this works well, and it's very efficient, and you get as much generality as you need, so you know that you can design your accelerator for the applications you care about, but it's very time-consuming. There's not very much that is automated by default. On the other hand, you have something like high-level synthesis, which is very automated. You start with a C program, put some fragments in it, throw it through a compiler, and up pops a fixed function accelerator. And these have been getting very, very effective over the years, and much more effective recently. But still, ultimately, the design that you're left with is fixed function. And so what we would really like, or at least what we're thinking about, is we have a framework that allows you to do some domain-specific design, allows you to have an accelerator that is general and work for other workloads, but and then also is somewhat special, and the designs are somewhat specialized. Okay, so I think those are basically the three principles that anyone would need in a programmable accelerator design framework. Right, the first of which being generality. The accelerators that you produce should be reusable across different kinds of workloads. So it should be maximally reusable across the different kinds of applications that you would want to target. And so to us, this means that what you would need is some kind of a general purpose accelerator ISA. So the accelerator ISA should capture the basic behaviors of the techniques that accelerators use to improve performance and efficiency. All right. The design framework should also be modular. So that means what that means to us is that the features that you have in that framework, they should be combinable in different kinds of ways, so that you can target different sets of applications. And you should be able to have just as much flexibility as you want. If you want a very flexible design, then you provide support for that, but we don't want to force people to have flexibility when they don't need it. And so what that means to us is that we need some kind of flexible representation of hardware. And in our case, we're developing, we built a graph-based representation of the hardware, and also we need a compiler that can understand what is in that representation, so that it can apply the relevant transformations to the program. And then finally, you would want of course, you want efficiency. You want to achieve the benefits of specialization and avoid von Neumann overheads. And to do this, we're limiting the design space exploration to a set of architectures that are known to be fairly efficient, called what we refer to as decoupled spatial architectures. And I'll tell you what that means in a moment. Okay, so at a really high level, our framework looks something like this. So it's called DSAGEN, and at the heart of it is a representation of hardware called the architecture description graph, or the ADG. And the ADG is a graph of very simple components that can be parameterized and combined in relatively arbitrary ways. So the components would be things like memory, processing elements, switches, and so on. And these are at a low enough level of detail where and they're kind of specified in a sufficient way that you could generate the hardware from this representation. But these primitives are not so low level that you would need to program each one explicitly. So the compiler can actually understand what's going on. And so in a sense, the ADG serves serves to define the accelerator, I say. So it defines all the features that are there in the hardware. And it also defines the format of how you would configure that hardware to do something useful. Okay, and then finally we have the compiler, which takes some applications and then we'll compile them based on the knowledge of what's going on in the ADG and what are the features available, and produce optimized kernels. And the final component of this is the design space exploration. And so the way that we think about this is that if we add a hardware, a model of the performance and a model of the hardware, so basically we can understand the performance of any application on an instance of the architecture description graph, then we can do a graph-based search to figure out what components in the hardware would be best for either a given application or a given set of applications. And so the overall what we're striving to do here is that we want to be the design that we produce to be general, also specialized, and have some amount of automation. Okay, so so that's basically the high-level idea. But I want to now start talking about a little bit of the details. So first of all, I think it's important to convey what kinds of architectures we are looking at here, and these are characterized by being decoupled spatial. And so, so first of all, let me explain what I mean by decoupled. So this is a very simple program on the left. It is just a vector multiply and accumulate. And and the decoupled data flow representation of that program is shown below it. And so what we're doing here is we are separating out the memory access in these little yellow boxes. And each yellow box kind of captures the entire memory access pattern that's there for that loop. And then those memory accesses will communicate with a data flow representation of the computation. So here, just a multiply and then add. Okay. And we're calling these memory patterns streams in the rest of the talk. And we'll refer to the compute part as the compute graph and the data flow graph. Okay, and so this is decoupled in the sense that the memory is completely separate, specified separately than the computation. And the reason that this is nice is that, first of all, we can specialize each part of the hardware. We can specialize the memory portion of the hardware and specialize the compute portion of the hardware separately. And they don't have to flow through the same pipeline, and so this can be more efficient. And also, this is a very natural way to do prefetching. Each one of these streams is decoupled from each other, and so they can run ahead as much as they need to. Okay, so here's an example, spatial architecture on the right. This is so let me explain what is here, right? So this is, these little red circles will be processing elements. So these are things that execute instructions. These yellow circles are switches. And so on these switches, we can route data and communicate between the processing elements without having to go through memory. And this is where we'll map the data flow graphs. And then this blue box is a stream controller. And so every unit of memory that we have in the architecture will have a stream controller. And it's basically an address generator and an arbiter, and it will arbitrate between the different streams that are mapped to it to perform memory access. And then there may be some synchronization elements that allow us to get the proper timing of computation. Okay, and so how would we map computation onto this? Well, we would just map the instructions processing elements and the communication into the switches, and then streams will be mapped onto the stream controller. Okay, and so the model of computation here is that the stream controller is going to be fetching data, piping data into the ports, the synchronization elements, and then as soon as we have enough data to do some computation, that will fire one instance of the computation. And this is much more efficient than a traditional programmable von Neumann processor, because we are pipelining instances of the computation but without having to do control and issue every instruction. So data is just naturally flowing from one processing element to another without having to decide what to execute. Okay, so then the final piece of this architecture is how you program it really in really the ISA. And so the control code here is executing an accelerator ISA. I'll describe it in a second. But the essential idea is that the control core will issue, it's kind of a traditional von Neumann core, but it will issue coarse grain commands, either to issue memory requests or to configure the data flow graph. Okay. And in doing so, we allow ourselves to be fairly general and use a general purpose core for control, but also to allow the accelerator to have this very specialized representation of programs. So this accelerator ISA, we call it stream data flow. It is, you can think about it as being a von Neumann embedded ISA. Okay. So the control program is just a typical von Neumann program, but embedded within it are instructions that will either the instructions for the commands for the accelerator. So those commands will either configure the data flow graph for the compute units, or send memory instructions to the stream controllers. Right, and so each one of these little colored boxes here represents one of those types of commands, either configuring the data flow graph or sending memory instructions. And again, the idea is that this allows us to have give flexibility in what kind of applications we can map. So we can map any kind of applications that we want, because we can map the program any program to the control core. But anything that can be specialized can be kind of communicated to the accelerator in a very efficient way. And the ISA for the accelerator is much more restricted. And it allows the accelerator to be more efficient. And we'll talk in much more detail about how this ISA works, and you'll have examples of where you can program it. All right, so that was just one, we just showed you one example of a spatial architecture. Actually, I should say, why are these architectures spatial, first of all, right? So they are spatial in the sense that the storage and the compute and the routing of data is all exposed to the ISA. And so the compiler is actually needs to make a decision about where and when things execute. This alleviates a huge burden from the hardware, and this is another reason why the hardware is so much more efficient than a traditional CPU. All right, so these are a few different examples of pieces of hardware that we could specify with our flexible representation of hardware called the ADG. We can have something that is, for example, in the style of the Mary architecture, which is an augmented reduction tree. We could change the graph and represent something that is more close to a plasticine style, which more or less looks like SIMD units, but with some interlane communication. And so these are all fairly flexible architectures, but there's no reason why we can't specify a more domain-specific architecture. So if we just eliminate the programmable switches, we can have a much more fixed function data path, if that's indeed what we desire. I also want to make one final point about the design space. So so far I showed you just different designs that have different topologies, and that's cool that we can have different topologies. But what we're trying to do is more than that. We want to also provide the ability to change the execution model of the underlying hardware units in a kind of fundamental ways. So we want to be able to change the behaviors of the processing elements and even the memories. So there's a lot to get into now, but I want to give you one high-level example pretty quickly so that you know what I'm talking about. And here, basically, I'm going to show you a few different kinds of processing elements that have different trade-offs. And all of these could be chosen or combined in different ways in the framework. So if we want to produce a really simple design, we might choose to have a statically scheduled single instruction PE, kind of the thing that you would find in a systolic array. It's basically a function unit, some muxes to select inputs if you have a routing mesh, and then maybe an accumulator. So basically a systolic processing element. This is very, very efficient. There's almost no overhead, but there is fairly limited support for control flow. And sometimes that's important. So we can have another kind of a processing element that adds back pressure into the network and then allows you to make different decisions about back pressure based on the result of the computation. Now it turns out if you allow the support in the processing elements and also the switches, you can do certain kinds of computations, certain kinds of control flow that you couldn't do before. So for example, this kind of a processing element is very good at doing joins. Do joins very efficiently in the processing elements. But of course, it costs you a little bit more area. And if you want really, general control flow support, well then, you could go all the way and have a multi-instruction PE that allows you to schedule instructions out of order. And that would give you the most flexibility, but it would also, cause you to incur more power in your overheads. And so we want the framework to have this capability of being able to compose these different elements together and differently depending on what kind of applications that you care about and you're targeting. And of course, this introduces this very complex challenge where the compiler now needs to be aware of what kind of processing elements you have. And actually, depending on what is there in the ADG, the compiler will, for example, for the second type of processing element, it will perform a unique kind of a transformation to the program in order to take advantage of it for the applications where you could do so. Okay, so that's just one challenge that we have to solve. Within our framework, we have a couple of different approaches for programming. One is based on just intrinsics. So each one of these commands, these kind of coarse grain commands that you saw before, will basically correspond to an intrinsic. So you have intrinsics for configuring the data path, also intrinsics for specifying memory accesses and connecting them up to the computation. So this is a little bit, this gives you the most control over what you're implementing and how you're parallelizing the program. But it would allow you to, but it's also very tedious, right? So we also have support, and we implemented a Clang LLVM compiler that will take a program annotated with a few much simpler pragmas, and these can be, and this is a much simpler programming interface. Okay. All right, so putting everything, and we'll show you how to program in both ways. We'll spend more time in the intrinsic programming because it teaches you what is going on inside these architectures and what their limitations are, but we'll also show you how to do the pragma-based programming as well. All right, so putting all this together, our framework basically has, like I said before, has an architecture description graph at the heart of it. We have a few different ways to specify ADGs, but the one we'll teach you about is the Scala-based ADG, and as well as Scala-based DSL. From the ADG, we can run hardware generation to generate the low-level RTL, chisel, and eventually Verilog. This is integrated with Chipyard, and we can produce a generated design integrated with Rocket, core from Chipyard, and the other features of Chipyard. This final part is the Chipyard integration is not released yet publicly, but we'll be doing so hopefully over the next number of weeks. Okay, but if you're interested in this part, let us know, and we can give you early access to it. Okay, so then what about programming? Except we have a C plus pragma-based programming interface, kind of like high-level synthesis would use. We have implemented a Clang LLVM compiler. It's going to read the architecture description graph, understand what's there in the hardware, and then it will produce, and then it will apply certain sets of transformations and split the program into the control core program, which has core string stream commands, and then also into data flow graphs. And of course, you are free to specify these manually if you don't trust the compiler. Right, these data flow graphs are then going to be scheduled using a spatial scheduling algorithm, and that basically does the mapping between high-level representation of the data of the computation onto the actual generated hardware ISA. This basically does a mapping problem, and then this will be embedded into the RISC-V binary. So we're using the RISC-V ISA for this implementation. This RISC-V binary can be run both on a simulator, and a very slightly different version of the binary will run on a DSAGEN generated design with a Rocket core. And then finally, like I said before, we have some support for design space exploration. So before I kind of hand things over to the tutorial part, I want to mention just a couple of things. So one is that so this slide showing you is a bunch of different features that we've implemented, and then kind of what level of maturity they are implemented at. So everything here is possible to do in simulation and through assembly programming, but a subset of that works with the compiler, a subset of that works with hardware generation, and then a certain set of features work end to end. And so we want to fill this up completely at some point, but obviously there's always going to be some features that are experimental. And so the reason why we're sharing this framework at this point is that we want, first of all, I hope it's useful, and hope it could be useful for different kinds of research. But we also want to find people that would be tell us what's wrong with it, tell us what we can improve, and also find collaborators. So we're really looking forward to that. Okay. So what are we going to do in the rest of this tutorial? This is the basic outline. We'll make it pushed back by 5 minutes because it started a little bit late. So Gian is going to tell us about, give us the introduction to the ISA concepts and show us how to manually program different applications. And then after that, Vidushi is going to tell us about the support for more data-dependent and irregular programming features. So these are some advanced programming features, and also tell us about how you would think about doing a multi-core program for the multi-core features that we have. And then after that, Gene is going to come back and tell us how to do everything that we talked about before with a much simpler pragma-based compilation that hides the details of what's going on in the hardware, makes it a little bit easier. And then finally, see how it's going to tell us about the Scala-based DSL for the architecture description language, and then a little bit about hardware generation. There's a few things that we're not quite covering in this tutorial, just because we didn't quite have enough time, so we won't really talk about the advanced compiler algorithms here, and it kind of means that we won't really get to like how do you extend the framework. But we have developed some, and we didn't quite have enough time to integrate all this, so we have developed some slides that we will be putting up on how do you extend the framework for different instructions and different kinds of commands, and we'll put that online after the tutorial. And we don't quite get to like going through design space exploration examples for the automated tools, but you'll know everything that you would need to just be able to run those commands. And so we'll also post some guide on that afterwards. Okay, so I'm now going to hand it over to Jian Wang. So Jian, are you ready to tell us about?
Yes, I'm ready.
All right, great, awesome. So I'm going to stop sharing. And yeah, go ahead.
Can you guys hear me?
Yep, loud and clear.
We can hear you.
Okay, hear me clearly. Let me share the screen. 1 second. Yes. Can you guys see my screen now?
Yes, I can see that.
Thank you. So thanks for my advisor's introduction. And in this section, I will introduce some basic principle of programming a decoupled spatial architecture. At the very beginning, I will give you an overview of the hardware in some more low-level details, as well as the programming interface through a simple example, vector addition. And then after implementing the vector addition kernel, I will show you the usage of our simulator, including reading the logs, troubleshooting, as well as using the logs to debug, to optimize your code. And let's start. And I don't really like the way on Zoom. I want it to be more interactive. And if you do not follow, maybe you can just make some reaction, just like a hand raising or something. And also we made a lot of update to the example repo. So make sure you make a git pull to get it updated if you clone it before today. And so let's start. And also one thing maybe I should mention is in each folder, there should be a answer.cc. So if you don't follow it, follow the programming, the guide of programming, you can still refer that to see, which step we are in. Thanks. So let's start. So to program an accelerator with the decoupled spatial execution, we should have a graph like this in your mind. So first, the computational instructions and the memory operations should be decoupled and represented in a data dependence graph, so that this graph can be mapped onto a spatial architecture composed by switches and processing elements. And the processing elements are for the computational instructions, and switches are for routing the data dependencies. And on the figuring on the right-hand side, the red circles stands for single instruction PE, and the purple circle stands for multi-instruction PE. And I will talk about the programming in the rest of my talk. And then, the memory, the data access are encoded in hardware intrinsics issued from the control host and to the address generator. Then the address generator sends the memory request to the memory. Then the data flows through this graph to execute. And sometimes we want a proper timing of data arrival of, in this case, we want the two operands arrive the other maybe at the same time. So a synchronization element is injected before entering the spatial architecture, and they are essentially coordination FIFOs. In this case, once there are data available in both of the FIFOs, a instance of execution on the graph will be triggered, and the data flow through this graph to execute this piece of program. And if there are multiple data to be triggered, adjacent instances will be perfectly pipelined on the spatial architecture. And in the rest of my talk, I will refer the synchronization element. I will use the terminology port to refer this component. Since in our software interface, it serves more like a memory port, an interface between, an interface to enter the spatial architecture instead of a synchronization element. Since we have a decoupled execution model, we also need a decoupled programming interface. And in this case, we first need a representation of the data dependence graph, and to describe the to describe this graph. And then we need a compiler that automatically maps this graph onto the spatial architecture. On the other hand, if we want to program the control host, what we need to do is to encode the data access with specific patterns like a threaded pointer, indirect memory access, and as well as the port communication in the local intrinsics. And the interface that bridges these two aspects are the port, as aforementioned. And in the next few slides, I will be talking about, I will first talk about how to program the spatial architecture and how the ports are exposed to the control host and to the control host so that we can encode the data access and forward it to its destination. So I want to know how many people downloaded our infrastructure set. So I want to know how many people downloaded our infrastructure set and are gonna try this out. So if you download our infrastructure set, you can just open it and go to the directory menu /01_vector_add and open the compute.dfg, which should be a empty file, and edit it with your favorite editor and type in this bunch of code. So this is a text format for this, for the data dependence graph shown on the left-hand side. And ideally, we should have something to map it into the spatial architecture, just look like this. And so, am I supposed to wait you guys for a while to?
Yeah, I would wait just a couple minutes and see if anyone has any questions about where to edit things or how to do it and so on.
There's a question asking about they're building a Docker, but cost target at round.sh because they seem to Gen5 was not in the Docker image.
Oh, if you cannot run the Gem5, you should, you should download our released binary, which is on the website. Which is on the website, and it's about 1.5 giga, and you just use the wget to download it and unzip it. You may have the DSA-framework, a folder like that, and you just source the setup.sh in that folder. You can export the Gem5 on your path, and you can run it.
An example he's showing is under the DSA example. And I think my collaborator Vidushi has just posted the link to the example through chat. Can check
Thanks.
that.
So yeah, if you haven't downloaded the binaries yet, it'll take a little while, and yeah, hopefully you'll be able to download them in the background and then catch up with us in a few slides.
The commands, the usage are quite simple as I designed the SDK. Really simple way to use it, and you can just leave it in the background, and let's move forward. So, to map this graph onto the spatial architecture, we should make the compiler, the spatial compiler, be aware of the spatial architecture. As aforementioned, the spatial architecture is very diversified with the different capability of the processing element and the topology and so on and so forth. And they are described in an architecture description graph, which is serialized in this JSON file. I mean, you don't need to know the details of this JSON file for now, and it will be described in my collaborator Sihao's section. How do you export this, and how do you, I mean, represent a spatial architecture in his scalar embedded DSL? I mean, both this compute.dfg and this JSON file are fed to the spatial scheduler. You can invoke, if you already downloaded our infrastructure, you can just type either of these commands to execute the spatial scheduler. And the spatial scheduler may generate two files. One is the schedule folder and another is the compute.dfg.h. And next, shall we just open the compute.dfg.h to see what the spatial scheduler dumps? So the compute.dfg.h should roughly look like this. And you may see a lot of pragmas here. The p underscore compute underscore a and b and c, which is the number of the ports. And these numbers will be used to program the control, the host control intrinsics. And the computer underscore config, which is a byte array. This array is the bit stream for the spatial architecture configuration. I mean, configure the spatial architecture is essentially load the routing information and the opcode to their config register. And I mean, you may see a string in it. It's a little bit cheating, or maybe it's not cheating for. It's a little bit cheating. It's only for the software simulation purpose. It hints our Gen 5 simulator to load the serialized format of both the hardware, both the spatial architecture and the mapping. And now I mean we can open the main.cc file and find the kernel function to fill in this intrinsics. So this intrinsic just load the bit stream from the array.
So I want to add something here. So you might find there's a compute config here, and in order to complete the software simulation, it will be replaced by the file names of the actual configuration. But if you want to do run the binary on the Rocket core, it will be actually replaced by a binary string in the configuration. So that is like basically the config bit to send to the hardware to config the program. So there will be like two different compute config variable there. So one is for the software simulation and the other one is for the actual hardware to run the program.
Oh, sorry, I forgot to mention, maybe, if you want this, the bit stream, you can enable the -b option flag in the SS schedule, command. Yes. Thank you for the complimentary. So, so for now, we already decouple the computational instructions and map that onto the spatial architecture. And the next piece is to forward the data to encode the data access in hardware intrinsics and forward it to the spatial architecture. What we want to do is to forward the array slice to their corresponding ports. And we do provide the hardware intrinsics for this purpose, which is SS_linear read. So starting with the given pointer, several bytes are forwarded to the given port, or we get several bytes of data from the port and write them to the corresponding to the given address. So you can just plug in these numbers into this intrinsics. Oh, the port is the macro, the numbers. I mean the macros defined in the compute.dfg.h. So here should be the how the intrinsics look like. Oh, sorry, if it's named in DSA in -Gem5, but the port exports Gem5, a very simple solution is to add a soft link from the Gem5 to DSA Gem5. I apologize for that bug. Maybe, I mean, I suppose it should be fixed yesterday, and if it's not fixed, you just make this simple solution.
Maybe, can you type the command for Lin to link it?
Which is ln-s Gem5 for DSA Gem5. Should from source to the destination, right? It will create a DSA-Gem5 link, which represents the Gem5 in a folder. I apologize for this bug. And I mean, so for now, we already decoupled the computation onto the spatial architecture and encoded the memory access in intrinsics. So what's the next? What's the last missing piece to program a vector add? So in this case, the last missing piece is how to synchronize with the spatial architecture between the spatial architecture and the control host. Say the control host assign a bunch of jobs for the spatial architecture to do, but the control host doesn't know when the spatial architecture is done. So we provide a intrinsic as a barrier, SS wait all. So this intrinsic may block the execution of the control host until the spatial architecture gives a feedback. Say, I'm done with all the computation. I'm done with two things. All the computations on the spatial architecture are fully drained, and all the memory, all the bookkeeping information of the active memory access are retired. After this is done, this SS wait instruction will retire in the host, so that the host can move forward. And besides this intrinsic, I have two things I want to mention. The first is that all the memory streams before the wait barrier are concurrent. In the hardware, they are executed in a round-robin policy, and I mean, these instructions are concurrent, so no order are guaranteed of this memory read writings of this memory read writes. So theoretically, you can just exchange the order of the intrinsic A, B, and C, and they are semantically equivalent, should be. And there's one exception. If you instantiate two memory access designated to the same port, there will be, I mean, they will be executed in the order they appear in the instructions. And later I will give you an example for this. So for now, we are done with programming the vector addition. We put everything together. So you have a data dependence graph like this in your mind, and you write this in the text format, and invoke the spatial scheduler to map it onto the spatial architecture. And the memory access are encoded in the host control intrinsics. And you just simply type this /run.sh main.out to invoke our simulator. So if you invoke our simulator, maybe it takes about a minute to run.
Hey, do you want to give people just 1 minute to look at that overview slide to implement everything? They haven't done so. Maybe I can just give like one quick overview of everything that's happening in case you missed anything. Right? So this program at the top in main CC is the control program. So that's what's executing on the RISC-V core, right? And then the way this works is that you would first configure the, I think this is a typo G and you should say compute config and compute size. But in any case, you execute the configuration statement, and that will configure everything that's happening on the spatial architecture. It will configure that data flow graph. And then the following two commands, the linear read commands, are going to read some bytes from memory and put them into those ports, and we'll just read them in order that you specified. And then the write command, as soon as there's data available at the port C at the bottom, then it will write that into memory. And then the wait all command at the end is just the way of the control core waiting for everything to be complete. So as soon as there's no more activity on the accelerator, that command will unblock and the program will continue. And then the compute DFG is just, that's just encoding the data flow graph. In this case, just an add. Are there any questions or any trouble, besides the Gen 5 problem, any trouble coding this up? Did anyone successfully code this up? So if you want to run this program, presuming that you did code it, if you want to run this program, you would write the command /run.sh and then main.out, and that will both compile the program and run it in Gen 5. So let us know if you have any further trouble on that. All right, maybe go on since it doesn't seem like there's any questions.
Fuck. Can you guys?
We can still see your screen. We can still see you.
Okay. Just the other functionality of my Zoom dies. I cannot open the chatting room.
Oh, and we can still hear you, but your camera seems free.
Okay. I cannot watch you guys too either.
But that's okay. If you can play this, can you click the screen and to see if you can still play the slide?
So
okay, you can still play the slide as well. I think it's good.
Okay. Typing this by simply typing this command, you can invoke our simulator and run this application on the simulator. The log dumped by the simulator is a little bit long, but I will extract the most essential information for you. So to read this log, can you guys kindly open my main.cc and let's look at the main function. So in the main function, you can see the kernel is invoked twice. The first time is just to warm up the cache, and the second time is wrapped by a pair of begin and ROI, which means these are the region of interest that we are gonna profile by the scheduled by the simulator. And the SB underscore stats is a hooking command, is a pseudo command that dumps this simulation log. And we can see in the region of interest, it totally runs 530 cycles. And look at this number below. It is there are 512 CGRA instances. This means the graph execution is triggered 512 times since our vector length is 512. So this means our spatial accelerator executes the vector addition in a fully pipelined style, and but a little bit, more than 95% of time are spent on the computation, but the overhead are mainly from loading the bit stream to configure the spatial architecture and train the pipeline of the spatial architecture. So, if this piece of program is executed on a conventional CPU, you need to unroll the loop and with a really, really wide out of order issue window to achieve this perfect software pipelining. But we achieve this with a mesh of switches and processing elements accompanied with a single issued RISC-V core, which saves a huge amount of area and power, which will be provided in Sihao's, and this will be provided in Sihao's section. And another interesting number I want to mention here is the CGR instances per cycle. This means the instruction level parallelism achieved by this spatial architecture. And for this one, it's less than 1 because we only offload one addition on the spatial architecture, and then 96% of time it's active. So the average instruction parallelism on the spatial architecture is 0.96. And next, I will be telling you how to optimize this number, how to achieve higher performance on the spatial architecture. So instead of offloading only one addition on the spatial architecture, what we need to do is to offload more instructions, more additions onto the spatial architecture in a SIMD style. Doing this is really simple. You just need to increase the bandwidth of the spatial of the ports and duplicate the addition instructions, but the host control still stays the same, since the amount of data processed by the spatial architecture doesn't change. Oh, fudge, I'm still using the old intrinsics here. I will correct this, after this tutorial when releasing this piece of, when releasing this, this PPT. So you don't need to change the intrinsics. This is just a typo here. And after editing the compute.dfg, you can just do the same thing. You can just type the same command to invoke the simulator,
Jian, let me remind you that you have 4 minutes left, which will be 11 o'clock.
Yeah, maybe you can probably take an extra 5. So why don't you probably have 10 minutes to finish your section, Jian.
Okay.
So you may want to speed up a little, and
okay,
I guess
speed up a little bit. So, I don't want to rush, since the point of this tutorial is not, dump as much information to you as possible. So, in this case, since we do 4 additions each time, so the graph is only triggered 128 times, comparing with the previous 512 times. It's divided by 4, and the cycles also reduces. but the activity ratio, I mean, the cycles spent on the computation, decreases. In terms of the percentage and portion, it decreases because the overhead of configuration and training the pipeline is roughly the same. And the instruction level parallelism is increased because we offload more instructions onto the spatial architecture, and they're often very busy in the execution more than 85% of the time. So we are done with the vector addition, and so next what I will be talking about is the troubleshooting. So I mean, when invoking the SS weight or the intrinsic, we made a very strong assumption on the data processed by this data are forwarded to each port. Typically, they are perfectly the same. So we forward the N elements to port A. We also forward N elements to port B. But sometimes, if you didn't manage the memory access carefully, it's not true. We can we can make this case by simply comment out the memory intrinsic forward to port B, and the A port will be overwhelmed, but the B port is still starving, as well as the C port. So what will happen in our simulator is the status of the streams is shown above, and the status of the ports are shown below, and there are some elements in A port, but no elements in B and C port, and the stream for C cannot make any progress. So this information may hint you how to debug which stream is not correctly managed. So we are done with the vector addition. So a end-to-end example, a simple end-to-end example to program decouple spatial architecture. And next, I will talk about the vector normalization. So vector normalization is more like, I will introduce some more hardware features, some computational idioms that cannot be specialized by the hardware features we introduced in the previous example. So for the vector normalization, there were 3 idioms that cannot be well specialized by the hardware features we covered in the last example. The first is the accumulation. So the value, since we need to compute the norm of a vector, and the vector normalization, if we just simply write a DFG file like this, we need to, every time we need to train the pipeline and forward the value to the input port, which loses the meaning of using a spatial architecture to achieve a perfect pipelining. So here we introduce a signal accumulator to specialize for this computation idiom. So for the accumulator, which is essentially a adder, but one of the operand is from the local accumulate register, and the result of the addition will be used to update this register. But it introduces 2 questions for us. One is how should we reset this? When should we reset this instruction? This accumulator register, and another is when should we finalize the data? So we introduce the signal, and over here we only introduce 2 signals. So now 2 predication control. One is discard. Discard means the value will not be produced by the accumulator. So this means when the value of S equals to 1, the accumulator does not produce value to the port O. Another is reset. So when the value of S is 0, it will reset the register. And we want to effectively generate the control signal, and here we introduce a SS constant intrinsic for this, and the SS constant intrinsic generates n values, n same values to the given port. And here is a perfect example for the order of the streams, since both the ones and the zeros are forwarded to the same port S. And the first stream will be, the second stream will not be issued, will not be executed until the first stream retires. And the second thing is, the second thing, I mean, maybe I fuse the second and the third idioms together. So we have in total 3 code regions to offload onto the spatial architecture. We first want their, want the execution, their execution to be triggered independently. So we use several dashes to separate each sub data dependence graph, and so that this data independence graph can be mapped on, can coexist on the spatial architecture. And another thing for the inverse, square root inverse, it's a scale operation compared against the vector operation. I mean, they are less frequently to be executed, so they are mapped onto the temporally shared PE across multiple instructions. We just annotate this pragma to this subgraph, so it can be, it can be mapped onto the shared PEs. So the last thing is the communication across this, the communication across this offloaded code region. So we do not want to drain the previous spatial pipeline and synchronize with the control host, since the control host is a very weak single issue call. This may introduce so much overhead. So what we do here is to do it asynchronously. We introduce a intrinsic which forwards the data from the output port to the input port, which will go through the recurrence bus. We can do it for the first code region to the second code region, but for the second code region to the third code region, it's not. We cannot do this because as we aforementioned, we make a very strong assumption that every port should have perfectly the same number of data forward feed to. But in this case, we only have one element feed to the coefficient port of the third code region. So what happens here is we introduce another SS repeat port intrinsic. So this intrinsic, when instantiating a stream, the element in this stream will be repeated several times and then popped from the FIFO. So for example, a 1, 2, 3 stream will be, repeated in a stream like this. So we just inject this intrinsic right before the recurrence. So this value will be duplicated n times. So to sum up, here is what we have. To sum up, here is what we have for the vector normalization. We introduce the accumulator, the temporal region, and the concurrent sub data dependence graph on the spatial architecture programming side. On the host control side, we introduce the const, the recurrence, and the repeat port. So you can. If you do not have time to run this main.cc, you can use the run.answer.cc. You just /run.sh answer.out. You can roughly get this. You can get this simulation log. So it runs 278 cycles, and the CGR instance is a little bit buggy here, since in the first code region, the value is not finalized until the last iteration. So the first 127 iterations are not counted in the CGR instance. It's actually executed. So in total, we have 257 instances, and which is slightly less than the number of cycles. And to sum up, to sum up, our decoupled spatial architecture is able to get the near ASIC performance intuitively if we have ASIC with, the same number of the functional units and can execute this piece of code in a perfect pipeline. The only performance gain they get is to get rid of the pipeline draining and the spatial architecture configuration. Okay, I wrap up my part. It's a little bit wrong.
Yep, thanks, Jian. No, it's okay. We started late anyways. So yeah, we'll take just a 5-minute quick break here, and then we'll come back with Vidushi to tell us about some advanced programming features.
So I just stopped my screen sharing.
But yeah, we'd be happy to take any questions in the meantime.
So,
or any clarifications if you cannot run examples in the repository. Maybe this is a good time to just fix if there are if you're seeing some bugs while running the simple examples.
Jesus, my Zoom is stuck. So
I think when Vidushi starts, she'll be able to just stop your screen share, hopefully.
yeah. I mean, I just want to quit and restart my Zoom now.
Okay, go ahead.
Okay.傻逼 Zoom 占用这么高。
Hey, Gene, if you could mute yourself, that would be nice. Any other questions in the meantime? I think Graham's been raising some good questions in the comments here. Ragul asks, I would like to know the graph compiler that was used to create the DFG. So yeah, we have I assume you're talking about the algorithm that takes the data flow graph and maps it onto the spatial architecture. Is that what you mean by the graph compiler? Yeah. So that is in our source code. That's called the Spatial Scheduler. And essentially what it's doing, we have a few different versions of the Spatial Scheduler that we've worked on over the years. One version of the Spatial Scheduler is built based on integer linear programming. So it's an optimization-based scheduler and basically solves scheduling problem mathematically. We found that this didn't particularly scale up. And so as we've tried to look at larger and larger designs, we had to move to more heuristic-based approaches. So the version that is there in the framework right now is based on simulated annealing. So what it will do is it will try to, and over provisioning. So what it will do is it will try to map the graph onto the hardware iteratively, and it will, the basic principle is that it will allow itself to over provision certain resources while it's mapping the graph. So when you're starting out, you allow yourself to map, for example, to instructions under the same PE, even if that PE can only do one instruction. And that over provisioning will be penalized. And by kind of repeatedly remapping different processing elements and routing elements, you'll kind of progressively eliminate the over provisioning and come to something that works. So that's the version that is currently there. And yeah, we're always trying to make the spatial scheduler faster, because as you get to larger and larger data flow graphs and larger hardware graphs, the spatial scheduling problem gets really hard. And so we're currently actually thinking, in terms of research, we're thinking about how can we use machine learning to help guide the heuristics for spatial scheduling. So we're currently working on that. But yeah, but thanks for the question. Okay, I'm going to hand it over to Vidushi to get started. Yeah, so Vidushi is
I think there's a question asking about the ADG is represented in Scala. No, the ADG is represented in the JSON. So we will use Scala to describe the ADG, and we will generate intermediate representation to represent the ADG in a JSON format. So I will show you later. So that is hand over to Vidushi about the advanced DSA programming.
Yeah, so please, whenever you're ready, Vidushi, please go ahead. Thanks.
Vidushi, I think you unmute yourself. You have been muted.
Yeah, can you hear me now?
Yes, I can hear you.
Yes, I can hear you too.
Okay. Hello, everyone. So Jian just gave an overview of the decoupled spatial programming framework and also discussed about some of the advanced features that are required to support fine-grained dependencies. In this section, I will discuss the features that we support for irregular workloads. These include the features to support data-dependent control and memory. After those features, we will do a hands-on exercise of doing a sparse vector dot product. I will conclude the section with the full SPM SPV implementation along with a way to parallelize it across multiple cores. So in order to understand the challenges with irregular workloads, let's consider this sparse matrix vector example, where the key kernel is to find the dot product of the vector and the first row of the matrix. In order to do first row of the matrix, a common observation, as you can see here, which is also very popular in many scenarios, is that there are a lot of zeros in this matrix as well as the vector, and it will be highly beneficial if we could skip those zeros during computation. In order to do that, a common approach is to store these vectors and the matrix in a compact format of compressed sparse row format, and then do the dot product. In the CSR format, each of the vector or the row is expressed in the form of two arrays. First one is the index array, which are the indices corresponding to non-zero values. So these are 1, 3, and 5 for the vector, and the value array stores the corresponding non-zero values. In order to find the dot product of such two vectors, the algorithm involves maintaining 2 pointers for each of the index. And then based on the comparison of these 2 pointers, one or both of them are incremented towards the smaller element. When we found a match, the multiplication and accumulation is done. This process continues until we reach the end of the list. Now let's say we would like to implement such an algorithm in our DSA design. So for that case, we'll first write the vanilla C code where we will express the same algorithm here, where I and j represents those pointers, and index A and index B are the corresponding arrays. Here we are not doing multiplication, but just finding the matching indices in order to keep the example simple. To implement it on the DSA, we first need to extract the data flow graph. In this case, the data flow graph would first involve the comparison of these two indices. Now, based on the comparison of these indices, either of the pointers have to be incremented, as we can see in this if-else loop. So in order to calculate the next induction variable, which is not just an increment in this case, we will select whether to increment it by 1 or 0, and then calculate the next I, which will be used to access the next index A. This process will be similarly repeated for index B. Finally, when these indices are equal, then both the induction variable have to be incremented. Also, the matching index has to be sent as an output. So here we'll compare whether these are equal and then send them as an output. Now there are two challenges in this data flow graph that have not been solved by the features discussed so far. The first one is the memory dependencies or indirect memory access. Here, the next memory location accessed in index A depends on the value of I or j in the next iteration of the while loop. Such a pattern of A of B of I is pretty common in several other workloads, and therefore we provide a way to support indirect memory access in our DSA. The second challenge is the unknown length of this output stream corresponding to matched indices. The reason is because the number of matched indices is unknown and depends on how many matches we found during the dynamic execution. Since this is one of the limitations of the streaming data flow model, where you have to specify statically the number of reads and writes, just using the same streaming pattern will not work. We need a way to inform the hardware that the computation has ended and it should not wait for any more writes here. And therefore, we also propose a way where we can identify and do the steps when the computation is completed. Now I will discuss in detail how we support these features. First, let's see indirect memory access, where the semantics are of A of B of I. In this case, the access locations of the array A depends on the values in array B. So therefore here, therefore in our ISA, we expose a way where where a stream can be dependent on other data stream. In terms of intrinsics, we propose an SS indirect intrinsic, which has the same inputs as the normal linear read intrinsics, where you read a value into the input port based on the address and number of elements. However, it also includes another input, which is an indirect port. The indirect port is corresponding to BI in the previous example. So the values in BI are used to calculate the updated address, which will be used to access the data in the original array and output at the input port. So this was the way to support indirect memory access. We also need a way for a data dependent length. So what do we do? What we discussed was we would like to have a way to identify the end of the computation and then inform the hardware for that. So SS receive is one way which is useful to do that. So the semantics of SS receive is it basically takes in a port and a memory address. Here, this instruction acts as a barrier, which is waiting for the data from the port, and that data will be returned to memory address, and then the barrier will be released. What we use it for is this port A can often be a way can often only send the output when the computation is over. So basically, we will have a barrier until the computation is over, and then we can release it. This is different from the general wait all barrier, which waits for all the specified streams to be over. Here we are using a specialized condition to release that barrier. The second instruction that will be required is SS reset. What SS reset does is basically resets all the pending streams in the hardware. It informs the hardware that computation is ended and you should not expect any more writes or reads. Only thing it leaves around is the live data, which is already in the CGR. So using the intrinsics of indirect memory access and data dependent length, we are now able to implement a version of join. To see how we do that, let's go to the code. So the code for such an implementation is in this folder, which is in DSA examples manual 04_bad join. Now, in order to write the code, we have the computation graph in join.dfg and the stream code or the memory access code in main.cc. So we'll open both of these things. In join.dfg, what we have done is compared the indices, and based on the comparison, we have calculated the next induction variable I and induction variable j. And then finally, we'll see if there is a match, and based on the match, we will output a matched index. So that's there. The other, in terms of the streaming code, which is really using our new intrinsics, are these ones. So the first one is where we are using an indirect access to basically consume the next induction variable calculated in the data flow graph to calculate the new values which have to be input at index A input. And similar thing is done for next induction variable J. Finally, we'll do a receive from a port done to a done flag, and then just reset all other streams. Since we did not know the length of the match index, we'll initialize it with the maximum length of the streams. So now let's see what output it produces. For running this, we'll use our command .run.sh main.out. And now after running this command, we'll see an output. So here we see that the computation is completed, but the activity ratio or the ratio rate at which CGRA function units are working is low. It's 22%. Also, the mapped DFT utilization is also low, which is 19% in this case. So what is the reason for this? In order to understand the reason, let's go back to the data flow graph that we implemented in this case. This was the data flow graph where we were calculating the updated induction variables and then accessing the indices A and B. However, if we see it carefully, there exists a cyclic dependence while doing this calculation. And this is basically limiting the throughput of this data flow graph by the latency of the instructions involved in this case. So therefore, as you can see that there are 4 instructions or 4 buffer steps involved in this, we got the utilization of less than 25%. This can even go worse when you have to access memory for the next values. We propose a control processing. We propose a way to add control in the processing elements to avoid such a loop. For that case, we make an interesting observation here. What the observation says is that the value of next index A or B is not arbitrary. It will always be either the previous induction variable or just the next one. So which means that in the next iteration of the while loop, you will either reuse the value that you were using in the previous iteration, or you will use the value which is next in the array. Such a way is can be intuitively expressed in a streaming model where you are accessing the values in a sequence. And if we have a way where processing elements can optionally reuse the values or not, then we could just avoid this cyclic loop and implement it in this way, where if next index is not incremented, that means you will reuse the value, and if it is incremented, you will pop the value. So therefore, in this way, we can avoid the cyclic dependence and theoretically improve the throughput by almost 4x. And the other computations will remain the same. In order to understand how we support such a control in the hardware and also in the programming interface, let's consider this conventional CGRA processing element where each of the functional unit is receiving inputs from its multiple input operands. There might also be a register file which is maintaining some intermediate state. For example, accumulators may maintain accumulated value till now. What we propose is extend this typical CGRA processing element with a control lookup table, which will consume an input from an external operand or the output of a functional unit. And it will produce 4 kinds of control signals, which we find useful. These signals include reuse on the input FIFOs or the discard from the functional unit. From discarding the output of the function unit, it might also cause resetting the register files. In order to see how these control signals can help in execution, let's consider an example where function unit is compared, while the example LUT configuration is as shown here. The LUT configuration, so this is basically a CLT or a control lookup table, which is configurable. The LUT configuration is basically, it specifies what control signal to switch on when you receive this control input. In order to activate any CLT, the programmer has to specify such a CLT configuration in the data flow graph or the DFG computation. For the functional unit, we are using a compare functional unit which basically returns a predicate based on the comparison of these units. So if your input 1 is greater, it will return 1, while if input 2 is greater, it will return 2. If they are equal, it will return 0. When both of the inputs are equal to the infinity, it will return 3. This instruction is a little new instruction, but it is pretty useful in cases of spatial designs when you have such kind of a reuse functionality. I will explain the use of such infinite. This infinity is usually used to append the normal streams at the end to identify the end of the lists, which is pretty useful in identifying the end of the computation or when the streams should end. It will be more clear when we'll go over the example where in the example execution using these two configurations of a processing element. So let's say here you have these two input streams which are coming in. Now, based on the comparison of 12 and 13, the output produced will be 2. And now it will look up into the CLT and produce a control signal of reusing the operand of 542, which means it will, in the next cycle, it will not pop 13, while 12 will be popped by default. In the next cycle, as we can see, the infinity is at 541, while there are some data values at 542. Now you can understand the benefit of infinity, where because this infinity is always going to be larger than any data value here, it will always produce a control signal of reuse 1, which means that this will not be popped and the other stream can just flow in without any issues. So this enables all the streams to be done without any meta computation to be left over. So now the other stream will just drain in. And when both of the streams are ended, you will see infinity at both places. Then the output is 3, which basically identifies the end of the stream. In this case, it will create a signal of reset where it will just set the value of the registers to 0. So this was a typical comparison unit, which is also pretty useful in the index matching process that we were doing for the dot product. And we will now do it for a hands-on exercise. So let's move on to the hands-on exercise where we still want to find the matching indices, but now with the help of self-controlled processing elements. So just to reiterate, the data flow graph looks something like this, where you will compare the indices, and based on the comparison, you will put the reuse signal. Here we have shown another way here because the reuse signal is put on the FIFOs and not on the actual vector ports. Therefore, we have shown this different configuration. This is important to understand because these input vectors may be sending inputs to multiple processing elements where they would be independently applying such control signals. So, okay, so now for this data flow graph, this comparison operation is basically outputting the predicate for which condition of them is true. Based on that predicate, this minimum computation unit will basically output the value. So this predicate is used, and this predicate is used to apply control signals for both compare and the minimum operations. After the value is sent as an output, when the values are equal, it will be sent as an output. Now we also need a way to identify the end of the list. For that case, we'll just equate the value of compare output to 3, which as we showed in the previous slide that it is a signal of a sentinel or an infinity value. And based on that, we'll filter out the matching output, matching index, and also we'll use these receive and reset signals to identify the end of the stream. Now, so this is the overall graph, and if you would, now we would like to implement this case. In this case, so the way of implementing it would involve 2 steps. first, we would like to write the computation graph, which involves all the computations and the configurations of CLT. And also, we would like to specify all the memory commands, which are specified in yellow here. So in order to do that, let's open this folder of manual04 join, where we will write the data flow computation graph in join.dfg. And we will also append the control code in main.cc. So let's open this folder. So we had to go to 04 join. And then first of all, our first step was to write the computation graph. So here I have written most of the parts. Only part I have not written is to generate the predicate by the comparison of these indices. So basically you would like to do the merge sort. So basically you would like to merge the two indices and move the pointers based on the comparison. So I'll pause for 10 seconds for you to read the instructions, which basically specify that you would like to generate the predicate using the compare 64 instruction based on the inputs of index A and B. And you would also need to write a CLT configuration, which will consume the self, which is the output, and the LUT configuration will be written something like this, where these ones are the inputs and these are the signals, control signals produced. Please note that for reuse 1, we are using a short form of B1. Okay. Okay, so now let's start writing. So what we wanted to do was we had to generate a predicate, so that's an output. It's generated based on a compare operation, which is taking input as index A and then index B. It is producing a self-controlled signal, so you will write self, that's a format for self. And now we have to specify the control lookup table here, or the LUT configuration. So what we wanted to do was, so the pointer should move in the direction of the smaller list if you want to find a match. So what it should do is, it should move in the direction where your value is minimum. So let's see what control operation is going to give. So when the output is 1, that means operand 2 is minimum. So that means the pointer for operand 2 should move, while for operand 1, it should just reuse the previous value. So therefore we would write it will just reuse the previous value. And then similarly 2 will be output when output 2 operand 2 is 1. So we'll do this case and we are done. So that's the thing. And then in order to see if we did not make any errors in just the basic errors, we'll schedule this file. And to generate the configuration, the command for that is make the file name .h, which will basically generate the header file. As we did, as we can see that the program is scheduled now. Now let's go on to write the memory accesses. In order to write the memory accesses, we'll also keep our data flow file open in order to know what are the inputs and what are the outputs. So here, as we can see, that what we basically need to do is read two input streams at input index A and index B, and basically write the output from match index to memory. For done, we do not need to write the output because it is used for receive. I have already put the receive stream, but we would like to put the other streams for index A, B, and match index. And for these cases, we'll use the streams as shown above. Okay, so let's start writing. So what we basically want to do is we want to read index A stream. For that case, we'll use this SS linear read syntax. Okay, so now the syntax is something like this, where we have to specify the start address. The start address for index A is and A index 0. The number of bytes we want to load from memory. The number of bytes would be equal to the size of the array and the size of the data type, which is 64-bit. and also the port we want to read into. The port is specified using p_join, which is the name of the DFG file, and then the name of the port. Note that as we specified that along with the data, we would like to read a infinity value, which will be used so that all the streams can just flow in. So for this case, we will need to send a constant infinity to this port. For that case, the intrinsic is ssconst, where we can specify this port, the value that we want to send, that's already specified here, that's already defined here, which is a sentinel value, and it's just a very large number of 64-bit values. So we'll say it's sentinel here, and we would like to send it only one time. We can do this similar thing for the stream B and just replace these things by B here. Oh, I see. Okay, it should be A already. And so the length is Bn here, and it will be index B. Okay, now we have read those two streams of index A and index B. What we would like to write is the output, the matching index. So for that case, we will use the SS linear write as specified above. The port it will consume from is SSP, this is like matched end. And then the number of bytes we want to write. Here, since we do not know how many bytes we need to write, we will just put a maximum value that's possible. The maximum value of the maximum number of intersections you can get would be the minimum of the size of two streams. But here, just for simplicity, we'll just keep it as n, which is the maximum size of the index streams, and n, 8, and then it will output will be output 0. Since this will not be equal to n cross n multiplied by 8, it will be reset after finding the done flag. So now that we have written this, let's try to run this code. Oh, it gave some error. It gave some page fault error. Let's see. That means that we have accessed a data which is outside that array. We accessed index B at Bn multiplied by 8. And this is n multiplied by 8, and we are writing to output 0. Let's check the answer file for what error that we have done. Is it's reading a linear read at index A, and then linear read at index B, and then a linear write here. Okay. Oh, I think, sorry, I put the format of linear write a little bit wrong. So it was addressed here. So let's fix this thing, which will be like, you will have to remember the locations of these values. So you'll specify the address here and the number of bytes here. So let's try to run this now. So therefore it was taking the wrong address, and that's why it gave a page fault error. So when you run this now, you can see the activity ratio is 97%, which was 20% earlier, 22% earlier. So what we can see here is we can get the throughput of we can do the index matching at a near line rate. However, if you observe this mapped data flow graph utilization, it is 60%. It's not proportional to the index match. The reason for this is because the multiplication units are not always active. They're only doing some computation when they found a match. Therefore, this is the overhead of sparsity, where your utilization would still be lower because you need to spend some cycles in order to find the matching index. Ideally, we would like that we only load the indices that match and load the values. But still, we see a very high performance gain as compared to the previous implementation. And so that's the whole exercise. Overall, as I discussed, we were finding the matched indices. Now we will move to do the real dot product or SPM SPV and the multi-core implementation. For, for a single core, the only modification to the previous code would be like this, where instead of outputting the matched index, you will you will see the induction variable when the indices matched and use them to access the value arrays and do the multiplication. So here in the data flow graph, there are two changes. The first one is, since based on the matching indices, we need to find the values. It will require an indirect access of values. So indirect access is still useful. Another thing that we would require is to replace this with a counter. So the reason for this is we do not need the matching index. Instead, we need the induction variable where it matched, so as to index into the compressed value array. And since we do not know the induction variable, we can just use a simple accumulator counter to do that. I will not show this, but you can just run the example in 05 SPMV. And what we see is we can get similar performance as earlier. Here I'm showing the performance at density 1, where we are seeing a very high DFG utilization as well, since all the indices will match. When the density is lesser, the DFG utilization reduces. However, we are still able to maintain a good activity ratio. So now let's move on to the multi-core implementation on how we would parallelize multiple dot products and while doing a sparse matrix vector multiplication. For that case, for a scaled version, we implement a way where these DSA cores are connected by a mesh network. And and for connection to memory, they will be connected to some of the cores will be connected to main memory at the peripheral. We also use a common global stream engine, which basically generates accesses for main memory and sends them from globally instead of sending each of the scalar access from each of the cores. Now, in order to parallelize dot products, what a naive way would be to just allocate some of the dot products, some of the matrix rows to each of the cores, which will do a dot product between those rows and the vector. Such a simple parallelization strategy can be coded using the pthread interface in our simulator, which will look something like this, where based on the TID, you will allocate different matrix rows. And yeah. And then I think it will be like this row will be equal to the TID, and then you will do all of these computations. So, and then finally, when all the dot product computations are done, we will apply a pthread barrier at the end in order to know when the computations are done. Now, while doing this gives okay performance, but there are several opportunities when you are executing it in a spatial decoupled spatial design. And it would be, and also some of the features will be required when you are doing for the accelerator scenario. So therefore, we make our proposals under three topics. The first one is a common optimization where multiple cores are reading the shared data. So for example, here, multiple cores are reading the vector, and it can save a lot of bandwidth if we could just read the vector from memory once and broadcast it to all other cores. So that comes under core-to-core communication. And the second requirement is synchronization. Here, pthread barrier is a global barrier, while several fine-grained barriers may be useful when you only want to wait until some of the work is done. Finally, since these accelerator cores use a lot of programmer-controlled memories called scratchpads, it is often tedious to map the data to the multi-core scratchpad space. For that case, we propose a configurable mapping scheme just to ease the programmer's job. So let's first go over the communication primitives. In order to show that, we have shown the DSA cores as here. We only show the parts that may be involved in the communication. So here we are only showing the control core, scratchpad, and the vector ports. For an explicit communication, explicit multicast is useful in cases when, let's say, you want to all the cores want to work on some data and just consume those data. So it might not be useful to go via memory, while you can just go via FIFO based vector ports. So the intrinsic we support for that is SS remote port. What it does is basically sends the data from a specified output port at a core to all other cores which are specified by a bit vector mask, and the core ID for other cores is specified by the remote port. So therefore, for example, in this case, the core 1 will send data to the ports in core 2 and core 4, which are specified by the bit mask. Another type of communication which could be useful, which is like direct one-to-one communication, we allow that communication using a implicitly by scratchpad memory space. The basic idea is to keep the scratchpads in a global address space. So if you want to access or interact with any other core, you can directly interact by specifying the address which lies in that core, and that core ID can be known by some most significant bits of the scratchpad address. For supporting such communication, we can use the scratchpad read-write intrinsics. We have not explained in this tutorial, but we have a similar set of scratchpad intrinsics as the DMA reads and writes, and you can refer to them more in the source code. Then finally, we said that we would like to support configurable data mapping. For now, we only support a cyclic. For that case, we propose an intrinsic of CFG mem map, which takes 3 inputs. The first one is the partition size. The partition size, which specifies how much data to be put in a single core before switching cores. Active core bit vector specifies how many cores store that data, and map type specifies different kinds of mappings. For now, we only support cyclic mapping, but hypothetically, there can be other kinds of mapping where you would like to replicate data and so on. So for cyclic mapping, here it shows one example where you will have a partition size and then the next data will be stored in the other core. In this example, the active bit core vector involves all the cores, while it may also be just a subset of the cores. This may be useful when multiple cores are working on the same data and you do not want to replicate it across all the cores or make, so you want to store the data at some central location. Okay, so now that we have explained our multi-core primitives, let's go back to our SPMV example, where we observed that the vector was shared among all the cores. In order to exploit that observation, we will use our remote port intrinsic, where we will read that vector only for a single core, and then that data for that vector will be broadcasted to all other cores. So this mask is the broadcast mask, which is one for all the cores. In this way, we can save a lot of vector bandwidth. In order to see how much that helped, we implemented 2 kinds of versions of SPMV multi-core. The first version is where each of the core just reads both the matrices and the vectors. In this case, what we see is we can get some speed up, but the utilization is just 25%. While the utilization for single core was 45%. We see this drop because of the network bottleneck, which is caused because of the memory requests going over the on-chip network. However, when we moved to the multicasting vectors, we got a higher DFG utilization of 34% versus just 25%. You can also test this scenario or test how the performance changes with different threads or densities in this directory. I can go and just test it for you just once. So it's 07 SPMV multicore, where to run this, you just need to do run.sh, and you should see an output. It takes some time to produce an output because it's modeling different threads. Yeah, here. So you get this activity ratio and the DFG utilization of 36%. And to test this, you can go here and then see where we have used remote port. You can change your dimensions, number of threads, or densities, and so on. Okay, that's all from my part. Thank you.
And then for now, why doesn't Gian kind of tell us about how do you use our accelerators without having to do low-level programming, right? So this was the very low-level programming interface, but we have a way that makes it quite a bit easier. So why don't you go ahead, Gian, and talk about the compiler.
Good to be back. Share the screen. I mean, 1 second, let me move to the correct page of the slides. Yes. Share the screen. Yes. Screen two. Share. So can you guys see my screen now?
Yep, it looks great.
Okay.
We can see it.
Okay, so let's start the compilation section. So, I mean, in the compilation section, thanks to Vidushi to talk about the generality of our accelerator. So, I mean, our accelerator can cover a wide range of applications. So, the programming interface, the high-level programming interface for our accelerator should also be generic enough to describe a wide range of applications. Therefore, a domain-specific language is not that satisfying. So here we decide just to use C as our high-level programming interface. And also, if we want, we can still use this C representation as a backend of the domain-specific language. And the difficulty of translating translating a high-level abstraction to our decoupled spatial binaries is that the host control totally is totally rewritten. The semantics is totally transformed. So what we do here, what we do here to amortize the effort of compilation, we require some hints from the programmers. We need some pragma annotation. So we leave these three questions to the programmers. First, which region of the code should be offloaded onto the spatial architecture? Second, which portion of the, how the memory accesses can be decoupled from the, the instructions and encoded in this intrinsics. Last, which is how can we determine the concurrency of the code regions offloaded onto the spatial architecture? And to answer these three questions, we introduce the three pragmas to correspond to these three questions. And I will introduce these pragmas also through the vector addition example. So here is the first pragma, and can you guys open compile /01 underscore vector underscore add? Which is the compiler version, and you can open main.cc, which is the not annotated version. And the first pragma we introduce is pragma SSDFG. This pragma either annotates a loop body or a compound statement, which indicates the computational instructions are offloaded onto the spatial architecture under this, under the annotated body. And we provide two clauses to this pragma. One is temporal, which will annotate this, offloaded region. with a temporal pragma, they will be mapped onto the shared piece. And another is a syntax sugar unrolling. So unroll, which allows you, I mean, you just give it a number to tune the FU resource occupation on the spatial architecture. Here we just give it by 4. You can, I mean, just follow the annotation on this slide and just type in it. And the second question is, how can we decouple the memory operations and encode them in stream intrinsics? So here we provide a pragma called SS stream. It always annotates a loop, which hints the compiler that the memory accesses below this and below are restrict. By restrict, we mean, I mean, in a simple words, we mean the array A, B, and C, the pointer A, B, and C are different arrays, and the access of this array will not exceed its array boundary. So, and we also provide a clause to this to this pragma, which is non-block. Non-block means you do not want to synchronize with the host control when finishing this code region. And last but not the least, which is the ssconfig pragma. Ssconfig pragma always annotates a compound body. I mean, all the regions annotated by pragma ssdfg in this compound body will share the resource on the spatial architecture. But in this case, we only have one region annotated by ssdfg. And to apply this pragma, you need to wrap what we annotated just now with a pair of braces and put on the pragma. And for now, we are done with annotating the this piece of code. And I mean, do not run this example with this command, or you will get some random error, and which I will explain it later. So, I mean, after annotating this piece of program, what you need to do is first, I mean, what this program will undergo to become a executable binary is something like this. So first, it's parsed by our modified clan so that this additional information will be encoded in metadata in the IR body. And this IR body will be fed to a specialized transformation path to decouple the computation and the memory access and encode the memory access into intrinsics. And then, I mean, since the rewrite may aggressively modify the original IR body, it may cause some, causes some IR which should be cleaned up by some generic optimization. So we invoke the O3 optimization to clean it up. And after that, this IR is ready to code generation. We use the LVM's LLC to do code selection and pump the assembly code. I mean, so until now we are done with the LLVM stuff, and we then use the GNU linker to link this text format of the assembly code to binaries. Since when this project was initialized, LVM didn't have very mature support for RISC-V, especially for the binary linker. So we still use the GNU thing. And for now, you can just type this command to run this piece of code. And I mean, it will just give you a very similar or even exactly the same log as I showed you 1 hour ago. So I don't want to talk about that. I talk about something more interesting, which is the principle of the compilation, how the metadata are encoded and how the transformation path leverage this additional information to lower the to rewrite the code. So for the configuration pragma, it will be, I mean, when IR code generation, it will be generated in a pair of begin and intrinsics to annotate the region of the configuration. And for the additional information related to the loop will be encoded in the loop metadata. And our transformation path will analyze the instructions in this annotated code region by starting from load memory operations and end with the store memory operations, traverse the dependence graph, and the computation or instructions among this graph will be extracted and duplicated according to the unrolling degree. Here it's 4, so duplicated by 4 and generate a data dependence graph, and this graph will be fed to the spatial compiler. And the configuration intrinsics will be removed and replaced by configuration intrinsics. And as you can see, for this blue regions, the indices of this memory accesses are analyzed by LLVM's SCEV scalar evolution module to encode them in the intrinsics. And the loop, all the instructions in the loop will be removed, as you can see in the gray region, which makes an empty loop. This empty loop should be cleaned up, should be optimized out. So we invoke a generic optimization to clean this loop up, as well as its metadata in the red region. So for now, we are done with the principle of the compilation. And here we come to the second example, vector normalization. So annotating vector normalization is the first region of vector normalization is, I mean, quite simple, just like what it is in the spatial architecture. And no, I mean in what it is in the vector addition. And for the second region, we need a little bit rewriting. We need to wrap this region with a pair of braces and annotate this compound body with the pragma. And another thing we need to add is the non-block in the previous region's annotation, since the compiler may detect the accumulated value will be used by the second region. It will be forwarded to the second region through the recurrence bus directly. And if we inject a SS weight there, the second region's output, the norm port will have no destination to go. Then, I mean, the SS weight will hang forever and then give you a error. So we need to annotate the non-block to escape this. And for the third region, it's not interesting, just the same thing. And finally, we put this all together. So these three regions will be concurrent on the spatial architecture, and the inter-region communication will be lowered by recurrence intrinsics, and the memory access will also do that. And something maybe you can play with is to, I didn't cover it in the, I didn't cover it in my spatial in my slides because of the for the sake of time. But I mean, you can put unrolling clauses here to see the accumulator will actually generate a reduction tree for you. And so, I mean, you just run this piece of code and it gives you very similar performance compared against what we had in the manual version. It's slightly slower because I mean, we generated some redundant assembly in code to redundant assembly code for the generality of compilation, but it doesn't significantly change the performance. So what are you guys discussing in the?
So I think there's a person is asking what is the name of that LLVM path that performs an analysis on the array access pattern.
Oh, it's called the scalar evolution, SCEV, and I mean it's just a bunch of expression trees for the operators and various a expression tree node that's specialized for the loop-based version is a recursive addition. So it will give you the pattern, the stride of the pointer and the starting point of the pointer. So you can, I mean, recursively dive into this tree to, I mean, to peer each loop down for and use that information for our streaming intrinsics. Yes. I mean, a very interesting thing I would like to cover here is the modular compilation. As aforementioned, we have a very diversified hardware capability, and in our compiler, we should cover all these features. And sometimes we don't want it to be a superset. We just want a subset of the features. So we can use some flags to enable or disable these features. When disabled, a fallback transformation escapes this feature will be invoked. And for now, the features I can demonstrate in this tutorial are the temporal region, the recurrence bus, and the indirect memory access. So I use these bold words in the environment variable and set them to 0 to disable the corresponding feature. And by default, they are all enabled and try the workloads. So for example, for the vector normalization, if you just use temporal equals 0 and run it, you may see the performance is, 6 to 8 times worse than 5 to 6 times worse than what we had in the previous slides. Previous one, it was 278, but it's nearly 1700. Because if we disable the temporal region, all the code regions that's gonna offload it onto the temporal region will fall back to the control host. The host call may execute it. So it introduces synchronization and some very expensive arithmetic operations like square root and division also fall back to the RISC-V call. So, I mean, I can run these examples with you. Let me. So can you guys see my terminal? Is the font too small?
We can see it, but it's too small right now.
Oh, Jesus. Maybe let me set it.
You can just press the control and scroll your mouse. It will be larger. It will make the font larger.
Really? Oh yeah. Okay. I can make it even larger. Yeah. Are you guys feeling comfortable with this font size?
Looks great.
Okay, looks great. So compile. So I have two additional examples. The first one is they optimize the gem, and the second one is a sparse matrix vector multiplication. And in this case, for the gem, the idiom we specialized. So instead of doing a inner product of each element in the gem, we do something in a outer product fashion. So we update a vector, we interchange the outermost two loops, and we update a vector of value in the gem. And in this case, so the value, I mean, we keep a read from the same address and compute it in the spatial architecture and write it back to the spatial, write it back to the memory. So, I mean, we keep on updating the same memory address. So there's no point to do this portion, do this memory traffic. What we do here is just forward the value from the output to the input. Since we have enough instances to hide the latency of from the entrance to the output, so it can still be fully pipelined. But it requires the support of the recurrence bus. And also we need to annotate it with a non-block, since every time we do not want to block the join the pipeline. We want the pipeline to be, I mean, always, we do not want to join the pipeline. So if in this case, we just comment this out and disable the recurrence bus and run this 03 DSA 03 gem.out. Takes a while since I mean it runs 48K cycles, but if we enable the recurrence and make each update asynchronously, we do not want to synchronize it. It should give us, if I remember it correctly, it should give us 3 times speed up. Oh no, it's enabled. This one is disabled. Sorry, my bad. So if we disable the recurrence bus, and synchronize after each execution, it will give us maybe 100K cycles. But if we enable the recurrence bus, it just runs maybe 48K cycles. So here it runs 142K cycles because we need to synchronize and need to join the pipeline each time. And it also has a very heavy memory traffic. But if we enable the non-block and enable the bus, we will get nearly 3 times the speed up. This is for this example. And the second is for indirect memory access. If the indirect memory access parallel the indirect memory access unit is, so it's nearly 3 to 4 times the speed up. And the second example is CRS.cc. So it has the indirect memory example. It has the indirect memory access idiom, and our compiler may detect this and encode it in indirect memory intrinsics. And in this case, since for now our compiler only does the parallelism in our compiler only does the unrolling the outermost in the innermost loop level. So for now, I can only manually unroll this outer loops to get some parallelism. And so in this case, the compiler may detect the if I enable the indirect memory access, what will happen is it will, generate code with a specialized intrinsics. If not, it will just use the SS const to. It will just use SS const to send the scalar data. Let the host call access the memory and send the data as a scalar to the spatial architecture. So it will lead to maybe 2 times to 3 times performance degradation. So here I just use int equal to 0 to disable this. Let's see the performance. So just now the performance was 873 cycles, but for this one, it's more than 2200 cycles.
So do you think you can wrap up the section in a few minutes, three or 4 minutes?
So I think I'm done with the examples I want to demonstrate. So I think I'm done with the examples I want to demonstrate. So to sum up, I think our compiler is able to detect, a subset, since it's still under construction, a subset of the hardware idioms that can be specialized by our decoupled spatial architecture. And with the moderate performance degradation, mainly because of the generality of our compiler may generate some redundant control commands. And I think that's it.
All right. Any questions for Gian?
The verification method.
Tyler or on anything else?
Yeah. Or maybe
Gian, well, if no one else wants to ask anything, I was wondering if you could tell us, kind of while we take our 5-minute break, I was wondering if you could tell us a little bit about the design space exploration. You told us how to compile things already, right? And so what would it take for somebody to generate some programs and then try to create the optimal hardware design from those programs?
So maybe in this 5-minute break, I will be talking about something about our design space exploration. So our design space exploration typically does something like this. Let me find our. So it will extract the. It will extract a bunch of DFG graphs from the set of applications you want to specialize, and then this data flow graphs has its own trade-off on different hardware features like the dynamic timing. If the dynamic timing is not supported, it fall back to the control host. If so, it's reflected on the data flow graph, and also the indirect memory access, and so on and so forth. So it will generate multiple versions of our applications, and then our design space explorer may have a grid of the spatial mapping and the
Wait, so let me clarify. So you're saying that the compiler will actually generate multiple different kinds of transformations depending on what features might be available in different instances of the hardware.
Yes.
Um,
I mean, the Design Space Explorer may maintain a mesh, a grid of the, I mean, the instances of the applications and try to map them onto the candidate hardware. And on the candidate hardware, I mean, we also use a simulated annealing algorithm to evolve this candidate hardware by either adding some function, by adding or removing some components on the spatial architecture. And the mapping may either be affected or not. If it's not affected at all, we just keep it. If it's affected, our scheduler, our spatial mapper will try to fix it on the new hardware, saying maybe some functional unit is no longer available. It will try to find a new functional unit and route it to that. If cannot, so we will just update. If this cannot be done, we will just update the objective function, saying maybe this. Well, I mean, this mapping cannot be mapped onto this candidate. Fall back to a more conservative one to see if it can map. And we keep on repeat this process until the objective function converges. By converge, we mean maybe it is not updated at all in long iterations.
so how do you solve the problem of figuring out what is the objective function very quickly? Because don't you have to, compile the program and run it in order to know how fast it is?
Our objective function is performance per millimeter square or performance square or millimeter square, whatever. So for the performance side, as we aforementioned in the log, the key to achieve high performance on spatial architecture is the instruction level parallelism. So we have an analytic model to count the number of instructions to be offloaded on the spatial architecture, and estimate when generating the stream intrinsics. We estimate the overhead of feeding the data to this graph. So we can estimate the performance by having these numbers. So we know the performance. Then for the hardware cost, like the energy, like the area, synthesize so many standalone components like the switches, the processing elements, and we just use those numbers, plug it into a estimation model to do an interpolation to estimate the cost of each component, and we add them up. And it turns out that this method of estimation is accurate enough but not exact, because in the hardware, in the synthesized hardware, some register buffer should be injected to guarantee the timing. But since we just add every component up, this part of the power area is ignored. But it only
basically the relative trade-off.
Yeah, 5 to 10%. So we use these two numbers to estimate the objective function, saying how much cost I want to pay and how much performance I can get. Yeah.
Cool. Yeah, I think we'll also put some directions in our repository for how to run the Design Space Explorer. All right, so then I think we should transition to the final talk, which is by Sihao Liu. And Sihao is going to tell us about how one might go about designing one of our ADGs by hand, and we'll give you kind of the control to specify the architecture and the parameters for the architecture pretty simply. So yeah, so Siha, go ahead and take it over whenever you're ready.
Okay, can you guys see my screen?
Yeah, it looks great.
And before I start, I want to check, so can you guys also see my terminal? If you can see my terminal and you feel comfortable with the font size, you can like raise your hands through the Zoom so that I can see that. Okay, cool. So yeah, let's get started. Okay. So thanks Jens and Vidush's talks. Now you might have a basic understanding of what is data flow execution and how to simulate them in the level of software simulator. But you might still ask, what is the actual hardware architecture that we are targeting to? And what will be the proper way to construct them and evaluate them? So now I'm presenting to you the hardware stack of our DSAGEN, which will enable you to describe the hardware efficiently, evaluate them properly, and provide you an end-to-end research approach. So my talk will first introduce you an overview of DSAGEN hardware stack. In this part, I will introduce you the workflow of DSAGEN and some basic concept. The goal of my part is to teach you how to construct the spatial architecture by using our domain-specific language and generate RTL and have some power and area estimation so that you can iterate it on your own research. And then we will perform some modification to the architecture that we just designed and redo this again so that you can see the hardware overhead of the design and how it will affect the hardware and software trade-off. And last but not least, I will present you an end-to-end research approach so that we can actually integrate our Spatial Accelerator into Chipyard, which developed by UC Berkeley teams, and do some experiment on it. So you will be able to take a piece of C program annotated by our Pragma and go through the stream data flow compiler developed by Jen and generate the binary with the stream data flow instruction, and define your own spatial architecture and run the binary program on the spatial architecture integrated with RISC-V Rocket Core. So let's take a look at the overview of DSAGEN. The hardware stack is on the is on the bottom of the picture on the left-hand side. So what do we want from the hardware stack? Well, of course, we need to have a way to describe the hardware. So we have some hardware primitives like processing element, switch, synchronization unit, memory, and control core. Then what we want to do is that we need to tell the compiler that what kind of hardware architecture that we want the programming to, we want the program to run on it. So that we can compile a program on it. And the third thing is that we want to generate RTL, like Verilog, from the architecture that we just designed so that we can like complete the full digital backend work, like doing logical synthesis, layout, or even tape out. And last but not least, we want to take some insight from the compiler and to improve the hardware design. And that is where we do the design space exploration. But this part will not be covered in this tutorial. Okay, so let's get started. So first, I will teach you how to build a simple CGRA by using our domain-specific language. And before we doing that, let's take a look at the spatial architecture that we are actually building. So our spatial architecture have a RISC-V CPU connected to it and have a memory system. And the rest of it is what we call CGRA, the coarse-grained reconfigurable architecture. And for CGRA, it consists of a bunch of processing elements here, where you actually do the operation. And the operation requires input like operands, and it will produce the output. So we need to have a way to direct the inputs to the processing elements and direct the output. So here we have switch. And a bunch of switch will form a routing network here. And also we want to buffer the income string and we want to form the output stream and read it from the memory or write it back to the memory. So we have a synchronization unit called vector port, and the vector port will do the work of synchronization. And the rest of it is we have a memory system, and also we have a RISC-V core attached to it. So this is the overview of the hardware architecture. So basically, we are trying to build this in this tutorial. But before we doing that, before we do this complicated CGRA, we can actually be starting from some simple one, which only have 2 input, 1 output, and 4 switches, and 1 processing element. Okay. So here's the way that we define the input vector port. Before I started doing that, is there any questions in the chat? Chat file.
No, you should be good to go, I think.
Oh, okay, cool. So here's the way that we define the vector port. So you just write val vector port 1 and new SS node vector port. So you can see that there's a string inside. I need to open up my, okay. So there's a string inside the SS node. So you can treat this string as a keyword of our domain-specific language. You cannot write anything like a car or like a cat. It needs to be a specific word because it's connected to the backend of this language. And you can then define another one. There are 2 vector ports, and also you can define the third one, output port. So this name you can like write any kind of name you want. It don't need to be vport I1 or vport O1. And then we want to define switches. So the same, you can define 4 switches by writing 4 lines of code and put a switch as a string. So this string is a keyword, so you can put a string to the SS node so that you can have 4 switches. And last but not least, you can have a processing element where you need to give, where you need to define what kind of instruction that can be performed by this processing element. So you have to wrap up instruction and give the list of the sequence of instruction that can be performed by this processing element. So that's it. That's it. How we define the hardware module in our CGRA. So is there any questions in the chat here? Let's see any. I don't know how to see open chat when I do this.
So you can open chat by just highlight, like go to the bottom of your screen, and then there should be right next to the share screen button is a chat button.
I can open up the Q&A, but I do not see the chat. If you have a question, you can feel free to raise your hand.
There's no questions, but
okay, cool.
I'll let you know if there's anything for you.
Okay, cool. So this is how we define the hardware module in our CGRA, but we haven't connected them yet. So we need to build a connection, and the way to build the connection is also very easy. So you just before you're doing that, you need to define the overall name of your CGRA. So you have you can write my CGRA and new, it's being SS fabric. SS means string specialized. So it's a computing fabric which has string specialized, and you can define some default value like the data width. We want to have a 64-bit CGRA, so you can write like this. Then you need to put all of the connection inside the CGRA that you just defined, so you can connect like this way. So you just put a dash arrow so that you can connect the vector port to the switches, vector port to the switches, switch to the vector. So here's how we define the input and output connection. And also we want to have a switch connection to form the routing networks. And we add a dual direction connection between each of the switches. And we also want to route the operands and route the results out of into the processing element and out of the processing element. So we can write something like this. So 3 out of the connection is 1 direction connection, and the last one, the switch 4 to the processing element, is a dual direction connection. And here's where you output the result. Okay. I do not see any questions, so let's proceed. Okay, that's basically what you need to write to build a CGRA, and I will show you a demo later. And the code will be in our DSA frameworks / DSA CGRAGen, and this is the path to the program to the architecture defined program. And this is the overall program that you need to write. It's just like you need to put the package and import and have a object definitions and wrap everything into it. So you will have a CGRA. Okay. So now you have the CGRA defined, and you must want to know that what you can do from that. So before I doing that, the tool I will use is the sscat inside the binary release zip file that we distribute to you. You might want to unzip that release file, and what I'm going to use is SBT, and SBT is required to run the RTL generator and the IR generator. So if you are using the Docker file, I think the SBT and will be there. So what I'm going to do is just I will do the exact thing as you did. So I have the DSA release have already been unzipped. So in here I have a DSA release, zip file, and DSA frameworks. And before you do anything, you need to rename the DSA frameworks into another name, so that because we are going to clone the repo to do the work. So I'm going to do the same things. You just move the DSA framework to another tool, and you clone the things. Maybe you have already done those things. I just want to do the exact same thing so you can reproduce all of this. And you might also want to git clone the example. So you might have already do that. I just want to repeat all of the things that you need to do to build everything from scratch. And there will be an optional tool called GraphVid so that you can actually visualize the CGRA that you just built. So I have got that installed it already, but if you are using the Docker, I think there's no way for you guys to visualize the result. But if you are using your own machine, you can do this command to install the GraphVid. Okay, so that gets started. And this is the CGRA that we just built. Oh, okay, before I doing that, I need to remind you that you need to get into the DSA framework that you just cloned, and only pay attention, only update the DSA CGRA agent. Otherwise, you will like download a bunch of other code. So I will just cd into my DSA framework, and I only update the CGRA agent. So that will give you everything you need. Okay, so I have my DSA CGRA agent, and you can in the next you can check the program that I just present to you, which is called microdemo, and in this directory. So what we want to check is we want to check the source main Scala, and I open up the demo. Scala. So this is exactly the same things that you want to that you will write to describe the CGRA. Okay, so what we will do next is that we want to generate the IR, and the IR is actually the description file for the ADG. So what we will do is that we need to cd to the DSA CGRA agent. We need to index directory and open up the SBT. So what I would do is that I will open up the SBT under here, the DSA CGRA agent, and it takes a while. And the command that you need to run is run man, and put the package name, because I named the package real, and write the name of the object. So you need to do is get run man real.micro.demo, and it will give you the result. Okay. And you can check the IR generated. It's just a bunch of like a parameter list in a JSON file, and it tells the compiler that what kind of hardware that we want the program to run on it. And there are some like other information in that. You can check that, but I'm not going to do that. And you can see the generation of the IR has just finished, so we can create the SBT tool, and you can find there will be a JSON file together with a YAM file. they are identical but in different format. They have the identical information but in different format. So you might be interested to check that. And then we want to actually generate the Verilog out of the IR. So I still need you guys to see.
Yeah, when you say IR, you're basically talking about the ADG, right? This
Yeah,
is the
yeah, that's the same things. The IR is intermediate representation, and the ADG is architecture description graph, and they are the same things. So every time when I say IR, it's just ADG, a JSON file I'm referring to. Yeah. So we want to generate the RTL from out of the ADG, which is actually graph. And if you open up the IR, the ADG file, you can actually find that this is a graph because it defined a bunch of nodes and it defined a bunch of connection. So you can actually build a graph out of that. And then we want to city to the DSA framework, DSA CGRGen, and open up the SPD again. So I'm already in that directory. So I will open up my SPD. And in order to generate the RTL, the thing that you need to do is to runman cgra.driver.generator and just give the name of your ADG file. So it will be myir.cgra.json. And it will do some computation, which is calculate the config path. If you are interested in what the config path is, I'm more than willing to talk about it offline. So it's finished. Then you can see that there will be a Verilog file, which is called cgrafabric.v. That is the RTL file that you are looking for. So, okay, yeah, I showed you, teach you how to generate the ADG so that you can do spatial schedule and show you how to generate the RTL. Before I proceed, is there any question? Okay, cool. So let's proceed. And in the next section, I will show you how to do some basic power and area estimation based on the ADG file that you just generated. So what we need to do is that we need to copy the JSON file, the ADG that we just generated to the DSA example hardware. And if you just clone the DSA example repo, there will be some JSON already there. So what about we just stick to that file and DSA example. So you can see that there's a hardware loader there. So just city to the hardware, and there are a bunch of JSON file that you can generate it from the trio that I just showed you, and they will you can use the JSON file there, or you can just copy the JSON file, which is ADG that you just generated into this directory. So I'm not going to do the copy, but you can use the SS tool in the release zip file. So in the when I say release zip file, I'm referring to this one that it's about 1.5 gigabyte. And when you do the unzip, you will create DSA framework. But in order to do this tutorial, I renamed the DSA framework loader into DSA framework tool. So when you cd to this, you will find that there will be a setup script so that you can source, so that you will be able to have access to all of the tool that we just built. So you can try to find where is the SSCAD. It's right in the DSA framework. So now we are going back to the example and the hardware floater in the example, HW floater there. So what you need to do is just SS as SCAD and enter the hardware architecture description graph, which is a JSON file into it. So I'm going to use the mycgi.json, and it will give you some area and power estimation based on 28 nanometer technology. So what we do here is that we have we synthesize each of the blocks many times, and we build an analytical model based on that. Okay, so maybe you can follow what I did and you might have your own result, or you can try other JSON file under that directory. I'm going to proceed. Before I proceed, is there any questions that you guys might have? Okay, so I'm going to proceed. And the last thing is that I'm going to teach you how to build your own CGRA. And this is the CGRA that we just defined. And what if we want to have something like this? We want to add another processing element, a new switches, and a new input vector port. So, sorry. So what you need to do is you can cd to the DSA framework and do some cd to the CGRA, DSA CGRA gen, and you will be there will be a file there. So I will just use the file that I generated, the EDG. So you do you open up the source main Scala and the real package and search for the micro demo and do something here. So I will use the answer file because they're there. So I will not showing the answer to you guys. Okay, so this is the connection that we just defined. Oh, sorry, that we just defined, right? And we want to add what? We want to add a new vector. Oh, so what we just built is that what we want to build next is that we want to add a new vector port, right? So you can add a new vector port. And by doing this, all you need to do is that you need to decide what kind of what will be the name of the vector port. So I'm going to use the same naming style. I call it vector port I3, and it needs to be equal to SS node, and the type of the node need to be a vector port. That's it. That's how we define the vector port. And next, what we need to do is that we want to add a switches 5 there. So I'm not going to call it switches 5. I want to have a customized name. So what I want to call it is I want to call it switch funny. And also do the same things. That's it. And what next is that we also want to have a new processing element here, so that we can add a new processing element which can do divide. I want to say call it divide, PE divide, and new SS node as the same. And what you need to do is just write processing element. Yeah. And pay attention, you need to define the actual instruction that can be performed by this processing element. So you want to give this a field which called instruction, and you need to wrap up the instruction that it can do. So actually we support two kinds of divide, is unsigned and signed. So I'm going to use the unsigned, and that's it. And that enable you to add the instruction to the processing element. So now we have 3 new modules be defined, and what we're going to do next. Yeah, we are going to add a connection between it. So how we need to add the connection is that that we just wrap up everything inside the fabric that we built. So you can define the connection by using vector port I3 and connect it to switches from. Oh, sorry, I think I just typed. You connect the vector port input 3 to the switch funny, and you can add another connection here. So I think the brace need to be here. It's a little bit funky. And another connection will be from the switch funny into the processing element, we call divide. And the last connection, oh, we have another connection from the switch 1 to the processing element. So we can just write like this. We have switch 1, which we defined it here. If you can see my mouse, and we can do a connection like P and P.did. And we have the last connection will be from the P processing element to switch 3. So you can just write processing element to switch 3. And they are they are all of the 4 connections that we will build. So from the vector port input 3 to switch 5, which I call switch funny here, and from switch funny to processing element divide, and from switch 1 to processing element divide, and from the processing element divide to switch 3. So we have all of the connection be wrapped into this. So I can make it nicer if you want. That's it. So we have 4 directions here. And what we need to do next is that we need to give a new name to the IR that we will generate it. And there will be a comment out answer. And that's exactly the same things that I just write about. But the different names of the switch. I use a new switch in there. So what I will do is that I will change the name of the IR, which is the ADG, into this one. And I open up the SVD again. Sorry, I forgot the name of the object. What is that? Okay, the name of the object that I just built is micro demo answer. So you can fire up the SBT and do the IR generation same again. So you run man, and the package is real, and the micro demo answer. That's it. And fit. So you will see that there is a new ADG file, which is a JSON file under the directory. And yeah, that's it. That's all you need to do. So if you're following exactly what I'm doing, you should probably get the same result. If you have a different output, you can let me know, and I will try to figure that out. Okay, I will proceed. So you can do the same things, like doing a spatial schedule on the new CGRE that you just built, so that you need to cd to the DSA example hardware folder, and then you can actually visualize the schedule result. But you need to have the GraphViz installed in. So I'm going to do that. So I'm going to cd to my DSA example file and into the hardware. And you can see that there are about 2 DFHG files which describe the compute data flow graph and have some JSON file there, which is the ADG. So you can do a spatial schedule. I think it's the command is like this. So you can use the new JSON file that you generated and do a spatial schedule based on that. And this will also give you the hardware estimation as well. And what you need to do is that it will generate a viz file, and you can cd into this viz file, and there will be a gv file, which tells you the actual schedule, and you can visualize it. So you need to use this command. It's inside the GraphViz, and you can actually create a PNG file out of the gv file. So I'm going to do that and trying to run the. So I think the file name is not correct. I need to, because we just add a divider there, right? So I can do, what I can do is I add the PNG, and what it will be the input G file is this one. So I doing this my cgra.gv, and you can actually see that it will create the PNG file, and you can copy it back to your host machine and open up the PNG. But I will not do that, but just show you the result. So initially we have this CGRA, right? And by visualizing it, you can see that it's actually doing the add by taking two inputs and do operation in the function unit and route it to another switches and route it out to another an output vector port. And when you add a new processing element which can do division, you can actually map a division operation onto it. So you can take two, I think you can take two input, which is B and D. You can do division on the newly added processing element, route it to another switches, and this processing element will take to produce the results and another input to produce the add out of that, and the result will be routed through this routing network to the output vector port. And you can see the actual mapping of the computer data flow graph mapped onto your CGRA. And yeah, this is the part that we just added. Okay, so we finished the hands-on practice. Before I proceed, is there
can I just mention one thing about the previous? Can you go back one slide? So notice the visualization. So you see on the visualization of the hardware that there are there's like 8 slots for every processing element. And the reason why there's 8 slots is that you can actually map multiple smaller 8-bit operations to that same processing elements. We support subword, SIMD. Siha is going to refer to this as decomposability in the following slides, but basically we allow multiple operations to map to each functional unit so that you can, if you have smaller data types, you can use the hardware more effectively. Yeah. So that's why there's so many slots shown in the hardware graph. Okay, that's all I had to say.
Oh, okay. Yeah, I will proceed. So in the next section, I will briefly talk about the advanced hardware feature that we support. Before we do that, we need to the basic concept of the switch. And switch is really easy, just like a bunch of muxes with the buffer at the output direction. This is the easiest switches that you can define. And the number of input port and the number of output port is actually defined by the connection. And what is inside the processing element is that I think we have already introduced that in previous presentation, but in order to describe that, you need to describe the data width of it and describe the instruction that it can be operate on that processing element. So we have some function units, instruction buffering, instruction scheduler. And now what I want to introduce is the decomposability. So maybe you can look at the left DFG. So we take 4 input, which they are all 16-bit data type, and we want to produce the data type, which is 32-bit. But in hardware, what we actually have, we have a 64-bit input, but only 16-bit is valid. So you have a granularity of 16-bit, and one of them, 4 16-bit, but only one of them will be valid. And by doing the multiplication, we do not change the data type, and we will only produce one 16-bit valid result, and the rest of them will be not valid. And for the right multiplier, we do the same thing. So only one 16-bit result, input and output will be valid. But how can we produce the 32-bit result? We need to have a contactor, right? So the contactor will still be 16-bit granularity. The granularity of this contactor will still be 16-bit, but we actually have 2 16-bit output be valid. So you can have a 32-bit value, 32-bit result. And how we do that is that we have one of the input that the second 16-bit input will be valid, and the other one will keep the lowest 16-bit be valid. And what we need to do is that we keep one of them to be one of the input data as its original place, but we shift the input data by 16-bit by its granularity, so that we can have the inputs to be in different slots. So you can see that this one, the output value is in the lowest slot, but then we have it on the second slot. And this circle means switches. So we can actually do the decomposability we can support the decomposability inside the switches. And this is how we do that. We add a subnetwork shifter at each of the output direction so that we can shift it by its own granularity. But in order to do that, when you create the hardware, you need to add two new fields which you specify its granularity. It can be less than its own data width. And you can also define the subnetwork shift offset. So you can shift by 1 granularity or by 2 granularity. But if you just write 0, 1, 2, you can only have 3 output. You can only have 3 kinds of output, which is shift by 0, which means that we have it's at its own original place, and shift by 1 granularity or shift by 2. And you can also have decomposability in processing element. The only thing you need to do is that you can write granularity, which is not equal to the data width, so that you can have a different type of processing element. And you may also want to have sometimes the input data, sometimes the downstream will not process the data as frequent as the input data. So you have to have some buffers to buffer the incoming data and tell the upstream that do not send me more data. You will have a dynamic data flow control, and this is how we do the dynamic data flow control. We will add a FIFO at each of the output direction, and you can actually configure the FIFO, the depth of the FIFO. If you do not configure the depth of FIFO, we will use the default one. But the things that you need to write is to have flow control to be set to true, and you have a valid ready signal pass through each of the input-output direction. And for the data control is, I think in Vidushi's presentation, she has already introduced the data flow data control processing element, which means that you can control the data reuse or reset the accumulator or discard the result by its own result. That means that you have a self-controlled instruction, or use the input result as the input to access the control lookup table. That means input control operation. So all you need to do is just add the self-control or input control as a prefix to the instruction that you want to perform on this processing element. And we can define the mesh topology because we don't want to write 25 lines if we want to define the 5x5 processing element array. So we can actually allow you to do that. And there will be a utility for each of the SS fabric called build mesh. And you can just enter the number of row and number of column you want. So it will give you a mesh array, and they will be connected through direction connection. So you don't need to write all of those things that I just write in the previous presentation. And now let's see what we will have in terms of the hardware trade-off. So you can check the DSA example, and there will be 2 files called my CGRE delay depth, which is 16, and my delay depth will be 4. And you can run the same command ssget and enter these 2. And I want to use 4, and you have a power area estimation, and you can change to another one. So you will have a different power and area estimation. You can see that the synchronization unit is actually different because we allow the second one to have a deeper output, I think this one should be output FIFO. Sorry, I make a typo here. So you configure the data, the FIFO to be deeper so that you can buffer more data to have a better flow control. And the synchronization unit will be different. You need to have a larger output FIFO. And as the last part of my section, I want to show you briefly about how we integrate our hardware generator into the chipyard. So I'm not going to do the hands-on practice on that because the SS chipyard repo has not been released yet. And all you need to do is just follow the configuration defined by the chipyard, just include our accelerator as this way, so that you will have a stream data flow CGRA together with a Rocky core. And in order to generate the binary and make it run on our accelerator, you need to use our GNU tool and use this RISC-V64 unknown GCC to generate the binary by using this. And you need to, because a bare metal see, a program cannot be run on the Rocky core, so you need to link the kernel with it. And now you need to use the chipyard GNU tool and do the link, so that you will have a RISC-V binary, and you can run this command later and change the sub project to our accelerator, so that you can actually run the binary program on a Rocky core together with our accelerator. Okay, that's the end of my talk. And here will be the Q&A section. Is there any questions? I'm really happy to answer that.
Yeah, I know we haven't, I mean, this chipyard part is pretty cool. I know we haven't released that publicly, but you know, if anyone is interested in actually prototyping and getting the designs working with the real core, like we're happy to get that out even in the early stage of development. So just feel free to let us know. Yeah. Any other questions? Anything? I know we're kind of out of time, but if there's any other quick questions, we'd be happy to answer them. All right, great. Well, I think
Okay,
we can. I really appreciate you guys coming. It's very humbling to see you guys all here. We're definitely looking to improve the maturity of the tools over time, and really happy for you to send us bug reports or feature requests. Like that would be awesome, and also appreciate the great questions, especially Graham and Etienne. Like, thanks so much. And yeah, okay. So someone asks, is there any planned future activities for the DSAGEN framework? Yeah, so there's a lot of things that we're doing. Like I said, one of the things we're looking at is how do we schedule for bigger designs? A lot of the accelerators these days are tremendously huge, and so we're looking at machine learning techniques that can help us do scheduling. We're also looking into algorithms for how to do the hardware design space better. Now that our design space exploration framework, it works, and it can kind of figure out what is the right set of features, but it does take a really long time because it's kind of been naively adding and subtracting components. And so we're also kind of thinking about, well, how do we use machine learning or other techniques to do this science-based exploration better in the future. We would also like to think about using DSAGEN for FPGA-based designs. I think it'd be really interesting to compare DSAGEN designs with HLS, and kind of explore what the differences are between a DSAGEN design and something that's more fixed function. There's a bunch of other things that we want to do. One thing is we want to improve the memory system support. So right now we kind of have a single level of scratchpad. And I think in a lot of designs, especially machine learning designs, we're looking at, we'd really like to have a more advanced memory system that can get reused at multiple levels. And I think that means, at least one thing that means is you have a multi-level scratchpad memory system. And that'd be very interesting to automatically design that memory system for you. And then I'll say one more thing. I think right now we were targeting C, and C has its limitations as far as what kind of transformations you can do very effectively to it. And so we would also like to look at compiling to DSAGEN-based designs from higher-level DSLs, things like TVM or TensorFlow. That would be really interesting to compile to these designs, and probably you'd be able to generate a different set of designs, right? So that's a sample of the things that we're looking to do with DSAGEN. But yeah, there's a lot of work left to do, and we're happy to find collaborators to work with in the future. All right, so I think yeah, we're already running over time, so I will end it here. And yeah, thanks everyone, and look forward to seeing you guys in the future.
Thank you, guys.
All right. Bye, everyone.
Bye.